At the dawn of the 20th century, a scientific revolution transformed our understanding of the universe. Quantum mechanics emerged to explain the behavior of electrons, photons, and other particles that defied classical explanations. Unlike classical mechanics, where objects have definite positions and velocities, quantum particles exist in a state of probability until observed. Its principles underpin much of modern technology, from semiconductors in your smartphone to lasers in your CD player. To grasp the essence of quantum mechanics, we need to delve into its foundational principles. One of the central concepts is the wave-particle duality, which suggests that particles such as electrons exhibit both wave-like and particle-like properties. Another key concept is superposition, where particles exist in multiple states simultaneously until measured. Entanglement is perhaps the most intriguing and perplexing aspect of quantum mechanics, where the state of one particle instantly influences the state of another, regardless of the distance between them. Quantum entanglement is one of the most fascinating and mysterious phenomena in quantum mechanics. When particles become entangled, their quantum states are so deeply intertwined that the state of one particle instantly influences the state of another, no matter the distance between them. Entangled particles behave as a single system, with their properties linked in a way that classical physics cannot explain. This interconnected behavior has profound implications for our understanding of reality. Entanglement has been experimentally confirmed through various tests, most notably the Bell test experiments. Albert Einstein, one of the greatest physicists of all time, famously referred to quantum entanglement as spooky action at a distance. He was deeply troubled by the implications of entanglement, as it seemed to violate the principle of locality, which states that objects are only directly influenced by their immediate surroundings. Despite his reservations, Einstein's work on entanglement contributed significantly to the development of quantum mechanics. Subsequent experiments have consistently supported the predictions of quantum mechanics, showing that entanglement cannot be explained by any local hidden variable theory. Imagine two particles, born from the same quantum event, forever linked by an invisible thread. When two particles become entangled, their fates are intertwined in a way that defies our everyday experiences. Measuring the state of one entangled particle instantly determines the state of its partner, as if they were communicating faster than the speed of light. Entanglement forces us to confront the limits of our classical intuition and embrace the strange and wondrous world of quantum mechanics. To understand entanglement, we need to shed our classical intuitions about how the world works. In the quantum realm, particles do not behave like billiard balls on a table, but rather like waves spread out over space. When two particles become entangled, their wave functions become intertwined, forming a single unified description. Measuring the state of one entangled particle collapses the wave function of the entire system, instantly affecting the state of its partner. One of the most mind-bending aspects of entanglement is its apparent disregard for distance. Two entangled particles can be light years apart, yet measuring the state of one instantly determines the state of the other. This quantum connection does not involve any exchange of information between the particles. Instead, it arises from the shared properties encoded in their entangled state. Entanglement is more than just a theoretical curiosity. Its counterintuitive properties have the potential to revolutionize various fields, from computing to communication and cryptography. By exploiting the superposition and entanglement of quantum bits or qubits, quantum computers could solve certain types of problems exponentially faster than classical computers. Quantum cryptography exploits the properties of entangled particles to create unbreakable encryption keys. One of the most mind-boggling concepts in quantum mechanics is superposition, a state where particles exist in multiple possibilities simultaneously. In the quantum world, particles don't have fixed properties like position or momentum until observed. Instead, they exist as a wave function, a mathematical description encompassing all possible states. Superposition is not just a theoretical curiosity, it's a fundamental aspect of quantum mechanics with profound implications. To illustrate the perplexing nature of superposition, Erwin Schrödinger, one of the pioneers of quantum mechanics, devised a thought experiment involving a cat. Imagine a cat sealed inside a box with a diabolical contraption. According to quantum mechanics, the radioactive atom exists in a superposition of decayed and undecayed states until observed. This means that the cat, whose fate is entangled with the atom state, is also in a superposition of alive and dead states. Section 3. Measurement. Collapsing the quantum wave. One of the most perplexing aspects of quantum mechanics is the role of measurement. In the classical world, observing an object doesn't affect its properties. But in the quantum realm, the act of measurement fundamentally alters the state of a system. It's like trying to pinpoint the location of a soap bubble. The very act of observing it causes it to burst. When we measure a quantum particle, its wave function, which describes all its possible states, collapses into a single outcome. This collapse is not a gradual process but an instantaneous jump from a superposition of possibilities to a definite reality. Imagine the spinning coin suddenly stopping, revealing either heads or tails. This collapse of the wave function is a central tenet of quantum mechanics, known as the Copenhagen interpretation. It suggests that the act of measurement forces the quantum system to choose a particular state from the range of possibilities. However, how this collapse occurs remains one of the biggest mysteries in quantum mechanics. The measurement problem raises profound questions about the nature of reality and the role of the observer. Does consciousness play a role in collapsing the wave function, or is it a purely physical process? These questions continue to be debated and explored by physicists and philosophers, highlighting the profound philosophical implications of quantum mechanics. Section 4. The elusive nature of quantum reality. The concepts of superposition and measurement point to a profound shift in our understanding of reality. In the classical world, objects have definite properties independent of observation. But in the quantum realm, reality seems to be fluid, indeterminate, and inextricably linked to the act of measurement. This shift has led to various interpretations of quantum mechanics, each attempting to reconcile the counterintuitive nature of the quantum world with our everyday experiences. Some interpretations, like the Copenhagen interpretation, suggest that reality is inherently probabilistic, with measurement playing a crucial role in collapsing the wave function. Other interpretations, like the many worlds interpretation, propose that every quantum measurement causes the universe to split into multiple parallel universes, each representing a different outcome. This interpretation avoids the collapse of the wave function but introduces the mind-boggling concept of an infinite number of parallel realities. The elusive nature of quantum reality challenges our classical intuitions about the world. It suggests that reality may not be as straightforward as it seems, with profound implications for our understanding of the universe and our place within it. Section 5. Entanglement and Non-Locality. Bridging the gap. Entanglement, the spooky action at a distance that so troubled Einstein, is intimately connected to the concept of non-locality. This means that entangled particles, no matter how far apart, are linked in a way that transcends our classical understanding of space and time. It's as if they have an invisible thread connecting them, allowing them to communicate instantaneously. Imagine two entangled particles, separated by light years. Measuring the state of one particle instantly determines the state of the other, regardless of the distance. This instantaneous connection seems to violate the principle of locality, which states that objects can only be influenced by their immediate surroundings. This non-local connection doesn't involve any exchange of information at speeds faster than light. Instead, It arises from the shared history of the entangled particles and the correlations imprinted upon them at the moment of their interaction. It's like two dancers perfectly synchronized in a choreographed routine, their movements intertwined even when physically separated. Non-locality is a fundamental aspect of quantum mechanics confirmed by numerous experiments. It challenges our classical intuitions about the nature of space and time, suggesting that the universe is far more interconnected than we previously imagined. Entanglement and non-locality challenge our perception of a world neatly divided into separate, independent objects. In the quantum realm, the boundaries between objects become blurred, and the universe appears as a web of interconnectedness. This interconnectedness suggests that the universe is more than just the sum of its parts. It's a holistic system where seemingly separate entities are linked in a profound way. This interconnectedness has profound philosophical implications, blurring the lines between observer and observed, subject and object. The illusion of separation arises from our limited classical perspective, where we perceive the world through the lens of our senses. But at the quantum level, this separation breaks down, revealing a deeper level of reality where everything is connected. This interconnectedness has profound implications for our understanding of the universe and our place within it. It suggests that we are not isolated individuals but rather integral parts of a vast interconnected web of existence. The concept of non-locality challenges one of the fundamental principles of classical physics, that objects can only be influenced by their immediate surroundings. This principle, known as local realism, assumes that objects have definite properties independent of observation and that information cannot travel faster than light. However, quantum mechanics, through entanglement and non-locality, demonstrates that the universe doesn't always adhere to these classical rules. The instantaneous connection between entangled particles suggests that information, or at least correlations, can transcend the speed limit of light. This challenge to classical locality has profound implications for our understanding of the universe. It suggests that there may be deeper levels of reality beyond our classical perception, where the rules of space and time are different from what we experience in our everyday lives. The implications of non-locality extend beyond the realm of physics. It raises questions about the nature of causality, the relationship between cause and effect, and the very fabric of reality itself. The implications of non-locality are far-reaching, extending beyond the realm of physics and into our understanding of the universe and our place within it. It suggests that we are part of a profoundly interconnected reality, where seemingly separate events can be linked in ways we are only beginning to comprehend. Non-locality has implications for our understanding of consciousness. If the universe is fundamentally interconnected, it challenges the view of consciousness as a purely localized phenomenon confined to individual brains. It raises the possibility of a deeper level of interconnectedness between minds and the universe itself. Non-locality also has implications for our understanding of time. The instantaneous connection between entangled particles challenges our classical notion of time as a linear progression from past to future. It suggests that time may be more fluid and interconnected than we perceive it to be. The implications of non-locality are still being explored, and it remains one of the most mind-boggling and profound aspects of quantum mechanics. It challenges our classical intuitions about the universe and opens up new avenues of exploration in physics, philosophy, and our understanding of reality itself. For decades, quantum entanglement remained a controversial topic among physicists. While some, like Niels Bohr, embraced its bizarre implications, others, including Albert Einstein, remained skeptical. Einstein in particular believed that quantum mechanics was incomplete, that there must be some hidden variables we weren't accounting for that could explain the seemingly spooky action at a distance. To address these concerns and determine whether entanglement was a genuine feature of the universe or just a theoretical artifact, physicists needed a way to experimentally test its predictions. This need led to the development of Bell's theorem and the subsequent Bell test experiments, which revolutionized our understanding of quantum mechanics and the nature of reality itself. These experiments were designed to distinguish between the predictions of quantum mechanics and those of local realism. The classical view that objects have definite properties independent of observation and that information cannot travel faster than light. The results of these experiments would have profound implications, either validating the strange world of quantum mechanics or revealing hidden variables that could restore our classical intuitions. The stage was set for a showdown between two fundamentally different views of the universe. Would entanglement prove to be a real phenomenon, forever altering our understanding of reality? Or would it crumble under the scrutiny of experimental tests, leading to a new era of physics? In the 1960s, physicist John Bell devised a groundbreaking theorem that provided a way to test quantum mechanics against local realism. Bell's theorem showed limits to correlations between entangled particles. These limits, known as Bell inequalities, provided a benchmark for experimental tests. Violations imply the universe is not locally real, supporting quantum mechanics and entanglement. These experiments have been repeated with consistent results, confirming quantum mechanics and challenging classical intuitions. Bell test experiments probe the deepest mysteries of the universe. Bell's theorem is more than just a mathematical curiosity. It represents a profound shift in our understanding of the relationship between theory and reality. In classical physics, theories are seen as approximations of a pre-existing objective reality. Bell's theorem, however, suggests that our theories can have a direct impact on the reality we observe. By setting limits on the correlations allowed by local realism, Bell's theorem forced physicists to confront the possibility that the universe might not conform to our classical intuitions. The subsequent violation of Bell's inequalities in experiments demonstrated that our classical assumptions about reality are fundamentally flawed. This realization has profound philosophical implications. It suggests that the universe is not a collection of independent objects with pre-existing properties, but rather a web of interconnectedness, where the act of observation plays a crucial role in shaping reality. Bell's theorem also highlights the limitations of our classical language and intuition when describing the quantum world. Concepts like locality and realism, while intuitive in our everyday experience, break down at the quantum level. To truly grasp the nature of reality, we need to embrace new ways of thinking, new languages, and new metaphors that can accommodate the strangeness of the quantum world. The significance of Bell's theorem lies not only in its scientific impact but also in its philosophical reach. It forces us to confront the limitations of our classical worldview and embrace a more nuanced and interconnected understanding of the universe and our place within it. Section 4. Beyond locality. The implications of Bell test results. The consistent violation of Bell's inequalities in experiments has profound implications for our understanding of the universe. It tells us that the universe is not locally real, that it cannot be described by theories that assume both locality and realism. This realization has forced physicists to reconsider some of their most cherished assumptions about the nature of space, time, and causality. One of the most startling implications is that the universe is fundamentally non-local. This means that objects are not isolated entities but are interconnected in ways that transcend our classical understanding of space and time. The instantaneous correlations observed between entangled particles suggest that there is a deeper level of reality, a quantum web connecting distant points in the universe. This non-locality has profound implications for our understanding of causality. If events can be correlated across vast distances without any exchange of information, it challenges our classical notion of cause and effect. It suggests that the universe may be governed by principles that are still beyond our grasp, principles that operate outside the constraints of our everyday experience. The implications of Bell test results extend beyond the realm of physics, challenging our philosophical and metaphysical assumptions about the nature of reality. They force us to confront the limitations of our classical worldview and embrace a more holistic and interconnected understanding of the universe and our place within it. Section 5. Closing the loopholes. Refining the experiments. Despite the compelling evidence provided by Bell test experiments, some physicists remain skeptical. They argued that there might be subtle loopholes in the experiments that could allow for alternative explanations, preserving the possibility of local realism. These loopholes, while seemingly esoteric, were crucial to address to ensure the validity and robustness of the experimental results. One such loophole is the locality loophole, which arises from the possibility that the entangled particles might somehow communicate with each other during the experiment, influencing the measurement outcomes. This communication, if it were to occur, would have to be faster than light to maintain the observed correlations, violating the principle of locality. Another loophole is the detection loophole, which arises from the fact that detectors are not perfectly efficient. Some entangled particles might not be detected, potentially biasing the results. If the undetected particles were to behave differently from the detected ones, it could skew the correlations and lead to a false violation of Bell's inequalities. Over the years, physicists have devised increasingly sophisticated experiments to close these loopholes. They have used entangled photons separated by vast distances, ensuring that no signal could travel between them during the experiment. They have also developed highly efficient detectors, minimizing the impact of the detection loophole. These refined experiments have consistently confirmed the violation of Bell's inequalities, closing the loopholes and strengthening the case for quantum mechanics and the non-local nature of reality. Section 6. The enduring legacy of Bell's theorem. John Bell's groundbreaking theorem has had a profound and lasting impact on our understanding of the universe. It has not only revolutionized our understanding of quantum mechanics, but has also challenged our deepest philosophical assumptions about the nature of reality. Bell's theorem has forced physicists to confront the limitations of classical physics and embrace the strange and counterintuitive world of quantum mechanics. It has shown that the universe is not a collection of independent objects with pre-existing properties, but rather a web of interconnectedness, where the act of observation plays a crucial role in shaping reality. The legacy of Bell's theorem extends beyond the realm of physics. It has inspired new avenues of research in fields such as quantum information science, quantum computing, and quantum cryptography. These fields are exploring the practical applications of entanglement and other quantum phenomena, with the potential to revolutionize various technologies. Bell's theorem has also had a profound impact on our philosophical understanding of the universe and our place within it. It has challenged our notions of locality, realism, and causality, forcing us to rethink our relationship with the cosmos. The enduring legacy of Bell's theorem lies in its ability to inspire wonder, curiosity, and a deep sense of awe at the mysteries of the universe. It reminds us that the universe is far stranger and more wondrous than we could have ever imagined. From paradox to paradigm shift, the triumph of quantum mechanics. Quantum entanglement, from theory to experiment, showcases human curiosity and knowledge. It evolved into a revolutionary concept in modern science. Violating Bell's inequalities shattered classical physics, challenging locality and realism, revealing a strange interconnected universe where observation shapes reality. This shift revolutionized our understanding and opened new scientific frontiers. Quantum entanglement now drives technologies like quantum computers and sensors. Entanglement's technological renaissance. For much of its history, quantum entanglement remained confined to the realm of theoretical physics, a bizarre prediction of quantum mechanics that defied intuition but lacked practical applications. However, the last few decades have witnessed a remarkable transformation. Entanglement, once a mere curiosity, has emerged as a powerful tool with the potential to revolutionize various technologies. This technological renaissance is driven by our increasing ability to manipulate and control quantum systems with unprecedented precision. As we delve deeper into the quantum realm, entanglement is no longer seen as a spooky quirk of nature, but as a valuable resource to be harnessed for practical applications. This shift from theory to technology is fueled by the convergence of various fields, including physics, materials science, computer science, and engineering. Together, these fields are pushing the boundaries of what's possible, transforming entanglement from a theoretical concept into a technological reality. This technological revolution promises to reshape our world in profound ways, from revolutionizing computing and communication to advancing medicine and materials science. As we continue to unlock the secrets of entanglement, we can expect a future where quantum technologies play an increasingly important role in our lives. Quantum computing, a symphony of entangled qubits. Quantum computers utilize qubits, which can exist in a superposition of states. This allows computations impossible for classical computers. A quantum computer is like an orchestra, with entanglement harmonizing interactions. They could revolutionize medicine, material science, and AI. As we improve control over qubits, quantum computers will transform our world. Section 3. Unbreakable codes, entanglement, and the future of cryptography. In an increasingly digital world, security is paramount. Cryptography protects our privacy and data integrity. Quantum computers threaten traditional cryptography. Quantum cryptography uses entanglement for unbreakable codes. It relies on physics, not mathematical complexity. Quantum key distribution, QKD, uses entangled photons. Interception disturbs entangled photons, alerting users. Quantum cryptography can revolutionize secure communication. It offers unprecedented security for financial and government data. As quantum tech advances, it will safeguard our digital future. Section 4. Quantum teleportation, beaming information, not matter. Teleportation often evokes images of sci-fi, of objects or people instantly disappearing and reappearing. Quantum teleportation is about teleporting information, not matter. It transfers the quantum state of a particle without moving the particle itself. This is achieved through entanglement. Imagine two entangled particles, Alice and Bob, separated by a distance. Alice can transfer the quantum state of a third particle, Charlie, to Bob's particle. Quantum teleportation does not violate quantum mechanics. It has profound implications for quantum communication and computing. It could lead to secure, instantaneous quantum networks. Section 5. A future entangled, the transformative power of quantum technologies. As we venture deeper into the 21st century, we stand on the cusp of a new technological era. Quantum technologies hold the potential to reshape our world in profound ways. Imagine quantum computers solving complex problems in medicine and AI, leading to new drug discoveries and innovative materials. Imagine AI systems that surpass human capabilities. Imagine secure communication networks, impervious to hacking, privacy guaranteed by the laws of physics, sensors with unprecedented sensitivity, revolutionizing medical imaging and environmental monitoring. The transformative power of quantum technologies extends beyond specific applications. As we unravel the mysteries of the quantum world, we can expect a future where quantum phenomena play an integral role in our lives. Section 1. Entanglement's challenge to our worldview. The exploration of quantum entanglement, a journey that began with theoretical musings and culminated in groundbreaking experiments, has irrevocably altered our understanding of the universe. It has shattered the comfortable certainties of classical physics, revealing a reality far stranger and more wondrous than we could have ever imagined. Entanglement forces us to confront the limitations of our classical intuitions, those ingrained beliefs about the world rooted in our everyday experiences. Concepts like locality, the idea that objects are only directly influenced by their immediate surroundings, and realism, the notion that objects possess definite properties independent of observation, crumble under the weight of experimental evidence. This clash between our classical worldview and the realities of the quantum realm is not merely an academic debate. It strikes at the heart of how we perceive ourselves and our place in the cosmos. If the universe is not a collection of independent objects, but a web of interconnectedness where the act of observation plays a crucial role in shaping reality, what does it mean to be human, to exist, to experience? Entanglement's challenge to our worldview is not a cause for despair, but rather an invitation to explore new ways of thinking, new languages, and new metaphors that can accommodate the strangeness and beauty of the quantum world. It is a call to embrace the unknown, to embrace the mystery, and to expand our horizons of what's possible. Section 2. The unsettled interpretation of quantum mechanics. Despite its successes, quantum mechanics remains an enigma in its interpretation. Superpositions, entanglement, and observations spark diverse interpretations. The Copenhagen interpretation emphasizes measurement collapsing the wave function, yet it leaves questions about measurement and the observer's role. The many worlds interpretation suggests parallel universes for each outcome. This avoids wave function collapse but introduces infinite parallel realities. The debate on quantum mechanics highlights profound questions about reality. Embracing the quantum enigma. At the frontiers of quantum physics, we find a universe stranger and more wondrous than imagined. Quantum entanglement challenges our classical intuitions, revealing a cosmos woven by invisible threads. This interconnectedness extends beyond physics, touching consciousness and reality. If particles can be entangled across vast distances, if observation influences the universe, what does it mean to be human? We are active participants in the universe's unfolding story. Our thoughts and interactions may influence quantum events. Exploring the quantum realm promises more surprises, forever changing our understanding of the universe.